Taking on superbugs. Superbugs are bacteria that cannot be killed using multiple antibiotics because they have built up resistance over time. You may be wondering, why is this problem so serious? If we lose the battle to antibiotic resistance from superbugs, things like organ transplants, cancer treatment, and even infant care will become near impossible. And those are complicated procedures. For all we know, things as simple as paper cuts could lead to infections that kill us. The rise of superbugs is thus seriously concerning. One area of cutting-edge research to combat superbugs has been conducted by Dr. Eric Brown's lab at McMaster University, led by his student Somaya Zlitini. This video aims to demystify her exciting findings. Somaya's study's theoretical framework was derived from the work of the scientist Gerard Domack. In one of his studies, Domack screened a number of potential growth inhibition compounds, but he realized that none of them actually led to the inhibition of bacterial growth on a petri dish. However, when he tested the same compounds in an animal, he was able to restrict the growth of bacteria with a compound now known as Prontosil. Domack discovered that there is a difference between in vitro and in vivo growth conditions and nutrients. The medium on the petri dish had more nutrients as compared to the living organism, thus enabling the bacteria to grow. The idea of deferring nutrient availabilities in vitro and in vivo forms the basis of Somaya's research project. Somaya postulates that nutrient-limiting petri dishes are more reflective of the conditions inside a living organism than nutrient-rich petri dishes. Most current classes of antibiotics inhibit the growth of bacteria on nutrient-rich media. By analyzing nutrient-limiting media, Somaya's study could lead to the creation of novel and innovative antibiotics that are, in practice, equally as effective as the current class of antibiotics. Somaya's study began with a collection of 30,000 compounds that could potentially inhibit the growth of E. coli bacteria in a nutrient-limiting environment that contained only glucose and ammonium chloride. Essentially, each compound would be added to the petri dish of the bacteria, and Somaya would observe the growth of bacteria over time. In the end, she was able to find 340 actives. This means, of the 30,000 compounds, 340 of them were able to inhibit the growth of E. coli in the petri dish. Later, Somaya tried to see if she could reverse the effects of inhibition by adding back certain nutrients in the environment. Of the 340 active compounds, she was able to reverse the effect on 71 of them. These were labeled priority actives. Dr. Brown's lab hopes that these findings will lead to the creation of effective antibiotics that work well on nutrient-limiting environments.